So we are now going to discuss about the properties of the magnetic field lines. So here we are starting with the properties of magnetic field lines. Till the previous video we have discussed about the magnetic field as well as the magnetic field lines. Now before understanding about the properties, let us make the magnetic field lines around the magnet and then we'll discuss the properties. Now, the pattern in which the iron fillings has arranged themselves, we separate those iron fillings and we trace the path over which that iron fillings were attracted. So, the path was in a curved shape like this, and this is all around the magnet like this. So, it is all around the magnet like this. So, there are numerous magnetic field lines all over this thing surrounding the magnet. Alright, so these were the magnetic field lines that was traced. So let us here talk about the first property. First property is these magnetic field lines, they form a closed circular loops. All of them, they are closed circular loops, even these ones. The loop is very big, so we are not going to trace this loop, but they all are closed circular loops. Second thing is, which is very important, outside the magnet, lines, that is, outside the magnet, magnetic field lines travel from North Pole to South Pole. So outside the magnet, they are traveling from North Pole to South Pole. So if we'll have to put down the direction, then it is from North to South. So these are all moving from the North Pole to the South Pole. So this is leaving the magnet from the North Pole. Now it is entering from the South Pole. So if it is north to south, so it means that the magnetic field lines, they are leaving from the South Pole. They are leaving from the North Pole and entering into the South Pole. So if the magnetic field line travels from North Pole to South Pole, it means it is leaving from the North Pole and entering from the South Pole. So similarly over here, north to south, outside the magnet. So it is entering from the North Pole and it is leaving the North Pole and it is entering the South Pole over this side. So North Pole will leave the magnetic field lines, or we'll say magnetic field lines appear to be leaving the North Pole and it is entering into the South Pole. So if we want to like this, so it is entering the South Pole. So leaving from the North Pole and entering from the South Pole. This is what is the second property. Now, in this property, there is one more thing. This concept is outside the magnet. If we are talking about inside the magnet, the trend is opposite. So, inside the magnet, the magnetic field lines travels from the south towards the north. So, outside the magnet, north to south. Inside the magnet, it will be south to north. So, inside the magnet, it is from south to north. So, it will form a complete closed loop. So north to south, outside, south to north, inside, north to south, outside, south to north, inside, and similarly over here, this side. So outside the magnet, it is from North Pole to South Pole, it is leaving the North Pole, entering into the South Pole. Inside the magnet, it is from the South Pole to North Pole. This is the second property. The third property is that magnetic field lines never intersect each other. They never intersect each other. The magnetic field lines, they never intersect each other. This point we will discuss in detail right now. Alright, in a minute we will discuss this point, that why two magnetic field lines never intersect each other. There is one more important property, and which is the direction of magnetic field is given by drawing the tangent to magnetic field line. if we'll draw a tangent to a magnetic field line, it will give the direction of the magnetic field. This point we have already discussed in the previous part, but we are going to discuss it one more time. So the direction of the magnetic field line is given by drawing the tangent to the magnetic field line. Now, how is this thing possible? Say if we want to find out the direction of the magnetic field at this point. Now, why we'll have to draw the tangent? That is the most important thing. The thing is, in the case of a circle, only tangent is a point which touches the circle at a single point. Only tangent is a line which touches the point at which touches the circle at a single point. Means if say something is moving in an anti-clockwise manner, so it is undergoing a circular path. So if I want to find out the direction at this point, I'll have to draw the tangent, and this tangent will give me the direction of that rotating thing at this instant. Now at each and every instant, let us suppose this, then the direction will change, and again if I'm talking about this, the direction will change. So at each and every instant there is a change in direction, and that direction should be unique at each and every point. And same uniqueness is for the tangent. Tangent also touches at a single point, and at every instant it is going to change its position. So only thing which can give us the correct value is the tangent to the circular path. So if I want to draw or if I want to know the direction of the magnetic field at this point, I'll have to draw the tangent. Tangent in the direction in which the magnetic field is. So magnetic field is towards this side, so I'm drawing the tangent towards this. So this is the direction of the magnetic field at this instant of time. Similarly, if I have to find out the tangent at this instant of time, or if I want to define the direction of the magnetic field at this instant of time, field is moving like this, so I'm going to draw the tangent over here. So this is the direction of the magnetic field. At this point, this, at this point, this. So at each and every instant, the value, that is the direction, will be going to change. Alright. So there is one more thing about the uniform magnetic field lines. Let me talk about that thing over here. So uniform magnetic field lines. Uniform magnetic field lines. There are two conditions which are to be fulfilled in order to say a magnetic field line is uniform magnetic field line. One is they should be equidistant, and second thing, they should be parallel. If the magnetic field lines, they are parallel and the distance between the two magnetic field lines that is equal, then we can say those magnetic field lines are uniform magnetic field lines. So if I'm going to draw it over here, these are the magnetic field lines which are all parallel to each other, and this distance is all equal. All of these distances are equal. So they are equidistant as well as parallel. So these magnetic field lines, they are known as uniform magnetic field lines. Alright. Magnetic field lines which are parallel, they are parallel and they are equidistant. So these are known as the uniform magnetic field lines. Alright. So these are all the properties of magnetic field lines, that they form a closed circular loop outside the magnet north to south, inside the magnet south to north. Then is the magnetic field lines never intersect each other, we'll discuss this. And the direction of the magnetic field is given by drawing the tangent to the magnetic field line. Here we have discussed that thing. Alright. So this was all about the properties of magnetic field lines. In the next part, we'll discuss this point in detail. Alright students, so now we are going to discuss that point in detail, that two magnetic field lines can never intersect each other. So here let us consider two magnetic field lines intersect each other. Let us say two magnetic field lines intersect each other. We have made an assumption, and by this assumption, if we can find out that this cannot be possible, so it means this assumption is not true. So that is what we are going to do. We are just making an assumption that two magnetic field lines has intersected. So if this is one magnetic field line which is moving towards this is the other magnetic field lines moving towards this, and they intersect at this point This is known as the point of intersection. So this is the point of intersection. Alright. Now, at this point of intersection, I need to find out the direction of the magnetic field. So this magnetic field line is moving towards this. So I am going to draw the tangent because tangent will give me the direction. So according to this magnetic field line, this would be the direction of the magnetic field. So let us say this is the direction 1. Alright. Now according to this, what will be going to happen? According to this, the tangent will be this thing. Tangent at this point will be like this. So this is the direction number 2. So at a single point, there are two different directions of the magnetic field. At same point, that is the point of intersection, there are two different directions for same magnetic field. Now at same time, at same instant, this cannot be possible that a magnetic field will give the two directions. This will not be possible because at one instant of time it is not possible for a quantity to move in two different directions. So this is wrong. Now why this is wrong? Because these two has intersected to a common point which is giving the two direction. It means the assumption that we have made was incorrect. So this assumption is incorrect. So what is the correct thing? That two magnetic field lines can never intersect each other. Alright. So the two magnetic field lines, they can never intersect each other. And here is the proof. Alright. So in the next part, we will be going to discuss the more important questions, or we can say the more important concepts.